Okay, so great. So where we are now is we're sitting with du d psi. Okay, this is the derivative of the u field with respect to psi. So this is essentially the derivative of n1, the derivative of n2, the derivative of n3, and then these are the variables that with which you multiply the unknown displacements for which we will solve. Okay, so that's essentially that. So the only thing that's now left is to make sure that we understand what is d psi dx, so that we can compute the strain. Because remember, the strain we're going to be writing, we need to have du dx, and du dx we're going to write as du d psi dx. Okay, so we can relate this using the isoperimetric formulation, and so this is the result if you say x is equal to n1 times x1 plus n2 times x2 plus n3 times x3, and we choose x3 to be in the middle of n1 and x2, and then this reduces towards this a half psi plus a half. Okay, and so the x d psi is just a half, and so I can say then the x d psi is just 2. So this d psi dx and times the x d psi is what I'm going to multiply with each other. The x d psi dx is what I'm going to multiply with each other. So I could go from u to psi, and then from psi to x world, and then essentially what I end up with is a lot of these 2's over x. Okay, so and again you can just double check for the linear elements for that x3 in the middle between the two other elements is really just the range of the psi's versus over the range of the x's. That's the advantage of a linear. If the element the mid side was not in the middle, then this would not just be a constant, and we'll still look at that at some point. Okay, but for now I'm just giving heads up so where we're heading. So the n d psi dx, this is now the derivative with respect to x in the end. So that's what we have. Okay, so when I say partial u partial x, partial u partial psi partial x, this is now the derivative of u with respect to x, and we can all put it together nicely and say this is the derivative of the shape functions multiplied by this transformation from the psi to the x world. This is really the Jacobian. So in 1D it's just a single value, but in higher dimensions this is a Jacobian matrix or the inverse of the Jacobian matrix, depending on whether the Jacobian operates from psi to x or x to psi, how you write it. Okay, but the bottom line is this is the mapping between two coordinate systems. Okay, and this then gets multiplied by the unknown displacements, but this is the strain. So we call this everything here, including this d psi dx and all of these shape function derivatives, we call the matrix B. Although it's just a row vector in this case, in high dimensional problems this becomes a matrix, because in the end we're going to have multiple strain components. You can imagine this is now epsilon xx. In a 2D 3D case we would still have epsilon yy, epsilon gamma xy, etc. So we'll have all of those terms as well. But the point is, this is just to make sure that you understand we call this the B matrix, and these are unknown displacements, and this is just a displacement vector. It will always be a vector that we have. And if I multiply this 1 by 3 by this 3 by 1, then I get essentially a scalar out, and that is my epsilon xx or du dx. Okay, so that's what we have. So hence we can now always simplify this partial u partial x as bq. Okay, so you can always just write it like that. Now we get to the partial u partial w partial x, and we have to ask ourselves, what is it that we're going to see there? I mean, what do we expect to see? Well, the fact of the matter is we already have now a nice shorthand form for partial u partial x. It's just bq. What is the difference between the u field and the wu field? The only difference is the weighting is these coefficients there. In the u field we had q's there, now in this w field we have just w's, but the rest stayed the same. Okay, nothing, it was exactly the same form. So my expectation is that we just would see partial w partial x to be bw, and let's confirm that. Okay, so if I take the partial u partial x and write it as partial u partial z partial z partial psi partial x, sorry, not z, psi, partial u partial psi partial x, then I can say the partial w partial psi is just the derivative of the shape functions as we've had before. Okay, and then we multiply with different coefficients there, these constants that we need to solve for. Well, actually we're going to take the derivatives with respect to those later on to recover our system of equations. But essentially we can then take partial w partial x, we can write then as just adding in this the partial psi partial x term. that comes into play. Okay, and this is again just the B matrix. Nothing has changed. Exactly the same as the B matrix we had before. So partial W, partial X, we just write as BW. Okay, this is important. If you do that, we have now all the terms that make up this. So we have the stress term and we have the partial W, partial X. And if you look at the stress term, it's E epsilon, ED partial U, partial X, and that we know is just EBQ. With this strain, it's just BQ, and so stress is just EBQ. Okay. The partial U, partial X is just BW. Okay. This is a scalar, and this is a scalar, so I can write them all into the equation. Say, so the stress term is that scalar and that scalar. Because they're scalars, I can swap them around. I can take the transpose of this and write it as W transpose B transpose, and it's still a scalar. Okay. And I can just move this into second place because it's EBQ is still also a scalar. This allows me just to write it into a convenient form where I can see B transpose EB. E is my material, in this case E, and multidimensional case this would be sort of my plane stress, plane strain matrix, or my full constitutive matrix. But the bottom line is, because I have this B transpose B and the symmetric thing in the middle, I end up with a full-on symmetrical matrix. And the symmetry comes from the fact that I've assumed the same form for the W than for the U's, because from the U field that's related to the stress, I get a B, and from the W field I get a B, and that's where the two B's are coming from. So this is then by construction symmetrical if I make sure I choose my displacements and my weighting functions the same form. Okay, the implication of that is that we end up with a symmetrical stiffness matrix. That is important to understand. Okay, let me just so that's that aspect. Okay, so I think, yeah, so I can, let me just double check quickly where I want to. Okay, no, that's fine. Okay, so what we have then is we can write this now conveniently as our integral from 0 to 1 over the volume, but all of these things are now in terms of size. So we need to relate this volume now to our area and our x. That's what we can do, but then we convert these things now to things that are a function of psi. So what we want to do is, what is x? Dx is essentially dx d psi times d psi. Okay, and so what is dx d psi? Dx d psi is just 1 over 2. So that is what I have there. Okay, so this is what we've had from before, but this is now an integral conversion that we're doing there. And then the area that we have, that's a function of x. All the x's that you see in here, we can just plug in our isoperimetric form. This x is a half psi plus a half. We just plug it in, and we have now the area as a function of psi. Done. Now the integral goes from -1 to 1, because I have already got the scaling factor that says dx d psi d psi. This will make sure we convert this domain towards a integral between -1 and 1. Okay, now we can go and say, fantastic, we call this, what in between these, this whole integral between the W transpose and the Q's. So this is not Q1, it's just Q. We call this just the stiffness matrix, K. And it's called the stiffness matrix because it's got units Newton per meter. Okay, and we can go and confirm for ourselves that it's got units of Newton per meter. Let's just quickly go through it, just to make sure we're comfortable. Okay, and I just want to go through the derivation of let's just go through the units check, not the derivation, just the units balance, and see what we get. And I just want to make sure I sensitize you towards 1 over meter derivative that comes in that you have to keep track of. Okay, so if I think about EBQ, EBQ is stress. That is Newton per meter squared. Done. Okay, so that is given now for us. EBQ is just Newton per meter squared. Okay, what we end up with, okay, so that's the first thing, Newton per meter squared. I integrate over volume. Okay, so Newton per meter squared becomes Newton meter. Okay, I pull out the Q. Okay, so I pull out something with units meter. Okay, so then I just end up with something that's newtons, and it might look like this is then only newtons, but hey, we forgot about a 1 over meter. Where? The fact of the matter is, this B from the weighting function was also a spatial derivative with respect to x. It was partial W, partial x. So that's another 1 over meter that we can't forget about. So that's essentially what we have, is then that we end up with something that's in Newton per meter. Okay, this is what the units of this thing is newtons per meter. Okay, is that everybody clear with that? And so this is also just as a quick sanity check for yourself when you look at the strain. Maybe I've forgot to just highlight this with you. The strain's units we expect to be what? Unitless, yeah? So essentially, what I see is this Q has got meters, and this B contains the information about the spatial derivative with respect to x. That's a 1 over meter, and that's why this has got is unitless. Okay, so this is just to make sure as we go along, just double check that the units make consistent sense, then we can move on. So we know that this is now units Newton per meter, and when I look at this, I want to integrate this thing. If I write it out like this, I just want to sensitize you about two things here quickly. And the one is, this the x dti that we have here, okay, is a half. Okay, that's a half that we have there. But if I look at what I've written here, I see there's a 2 there. So we need to ask ourselves, what is going on? Did Nico make a mistake, or what's going on? Okay, so the first, the one thing that I want you to be sensitive about is when you look at this B matrix. This B matrix has a d psi dx in there, and d psi dx is 2 over 1. Okay, so that's a 2 that we have there, and there are 2 of them. Okay, so there's a 2 here in this B. There's going to be a 2 in front of that matrix, and there's going to be 2 in front of this matrix if I want to, that I could pull it out. Okay, and there's a half here. So if I take the 1, 2 and I multiply it with this half, it becomes a 1, and then there's 1, 2 that remains, and that's why we see a 2 there, because I didn't multiply it into this matrix. These terms in front of the B matrix I just essentially pulled out, and what we end up with is that 2. Okay. But it's important to understand this, because later on you can ask yourself, and I'm going to ask you to pay attention to this fact, is what would happen if the psi dx was not, for instance, a nice constant. Okay, we're going to still look at that. What will happen? Okay, so bear in mind, I'm giving you a clue now to pay attention as we go into the course, when you start looking at other things, what the implications would be. Okay, but the bottom line is, so this is what we end up with. So when the psi dx and the x d psi, when they're not constant, we can look at that at some point. And we're going to achieve that by making sure that mid-side node is not in the middle. Okay, what I end up with is this, and what I would like to then say is, what is the integration rule required to solve this? Well, I can see there's a, what is the highest order polynomial? There's a psi squared, there's another linear, and then I get another psi in from here, from the area. So it looks like it's a linear times a linear. So it's 3 linears multiplied to something that's cubic, and if it's cubic or third order, then I need an integration rule that is at least 2 points. Okay, and that will be exact. If I use 3 points, 4 points, I will get, and so I can do that numerical integration of this using Gauss quadratures. And again, I just want to say, just look at how many integrals we're doing. Lots of them. Okay, and then essentially I get the k, and then I can use this stiffness matrix in my calculations onwards and say, okay, fantastic. Now I get to the point. Okay, so that's it. And then I'm going to pause the video here, and then we can start with fractions in the next one. Okay, but what we see is this k becomes then W transpose k Q. That's what we see. Okay, let's go on to the next video.